So our goal for today is to take a kind of sidestep or return to the idea of estimating an integral. And I want to show you one of the methods that the pros use in order to estimate integrals. This is actually the method that your calculator uses, more or less. And that is going to be by using, instead of rectangles, we're going to use trapezoids to estimate the value of our integral. And by so doing, we will increase the accuracy while not increasing the amount of computation. Isn't that nice? It's the different sides. No, it's like long. So today's lesson is all about estimating integrals with trapezoids, and we're going to end up with a rule, which is the trapezoidal rule. Now, let me remind you of what a trapezoid is and its area. Remember that we have previously said...
Teachers, pardon the interruption. Please excuse the interact students.
So recall that a trapezoid is a shape that has two parallel bases. In geometry, you often drew those bases so that they were horizontal, but here we're going to draw them so that they're vertical. And the trapezoids that we're actually interested in are going to be trapezoids that such that the bases are going to be perpendicular to the bottom here. I'm going to label the bottom as H. H is going to be the distance between our two bases. And we're going to have B1 and we're going to have B2. And you recall that I argued previously that the area of our trapezoid is the average of those two bases times the height. And the reason for that is fairly simple. If I take and draw myself a line segment that is the average of those two bases, then what I end up with is a triangle here that is congruent to a triangle right here. If I cut off this triangle and place it right here, I end up with a rectangle whose height is B1 plus B2 over 2, and whose width is H.
Is that geometrically equal to using midpoint?
No, it is not. The midpoint rule that we have is going to be one where we take midpoints of the x's right here and find their corresponding heights. If my curve happens to be a straight line, then the trapezoidal estimation would be the same as the midpoint. But if it is not a straight line, if my curve does something like this, then the midpoint would give me this, the trapezoid would give me that. So I want to be clear that the average of these two bases right here does not give me any kind of midpoint estimation. Students will often confuse those two. Okay. So now, how does that help us? Suppose I've got a curve right here, and I wish to estimate the area under the curve from A to B, like so. And so I can write the area as a definite integral, the integral from A to B of f of x dx. This is exact. But now the question is, how could I estimate it if I did not have a formula for f of x, or if I did not have an antiderivative for f of x? Well, I would estimate it by partitioning my interval from A to B like so, and then I could choose a number of different schemes for finding rectangles, right? And one of those schemes was the left sum. You guys remember the left sum? On your papers, I'd like for you to draw the rectangles that would correspond to the left sum. And if I were to do a left sum, which we will call L, then I would add up from I equals 1 to n, and the choice would be the x value on the left, which is x sub I minus 1. So if A is x sub 0, I would choose f of x 0, and that would give me this rectangle right here. and then f of x1, f of x2, f of x3, and I never do f of x4 because at that point 0 through 3 cover all of my rectangles. So I add up then f of x I minus 1 times delta x, and that gives me a left-hand sum. The two things that I want you to pay close attention to are, first of all, the geometry of it. I've done a left-hand sum over here, and second of all, the way I accomplish it over here is by doing f of x I minus 1, taking the one on the left, times delta x I. Does that make sense to everybody? Now what about a right-hand sum? A right-hand sum is going to be same song, second verse, but this time instead of choosing the x on the left, I choose the x on the right, starting with x1 and going all the way out to x4. So that when I do that, my right-hand sum looks like this. And inside here, instead of choosing xi minus 1, I choose x sub I. Subscript x sub I. All the cool mathematicians call it x sub I.
When do they use the letter I?
I for index.
Okay.
I could use the letter J or the letter K. Those are common index values also.
What did you indicate?
Index and index. It's sort of like a do re mi fa sol la ti do. At some point you get to like la note follows so. So J, a variable like I. Okay, so these are two different rectangular sums that we did. If we had done a midpoint sum, then inside here we would have f of xi minus 1 plus xi plus xi all over 2. So we would use the average of the x's to locate our height.
Because I forgot, can you explain that I minus 1? Why do we have that?
Because number these rectangles, 1, 2, 3, 4, and number your x's starting at 0, you get x0, x1, x2, x3, and x4. Notice it takes 5 x values to define a partition with 4 subintervals, right? So if I want to do the left-hand sum, to choose the one on the left of each subinterval, for the first subinterval, I need x0. For the second subinterval, I need x1. For the third, x2. For the fourth, x3. In other words, for the ith subinterval, I need x sub I minus 1.
So why do we have x sub I for the right?
For exactly the same reason. When I do the right-hand sum, I need to use the one on the right. And the one on the right for the first subinterval is x1. And the one on the right for the second subinterval is x2. And all the way down to the fourth subinterval.
So you don't
You're doing it on the right instead of the left.
then would that change? Would that number change if delta x sub I change?
It does change. What's happening with these indices is we are counting from 1 all the way to n. So if I were to write this out the long way, the right-hand sum looks like this. F of x1 delta x1 plus f of x2 delta x2 plus all the way out to the last one, f of xn delta xn. That's what this sum means. Okay? And I is the index that is counting those x values and counting those deltas as we go. Well, this is all fine and good, but now what I'd like to do is I'd like to do this with trapezoids, and here's why I'd like to do this with trapezoids. When you look at the right-hand sum, the left-hand sum in blue, what do you observe about the left-hand sum in terms of accuracy? It's larger. Yes, it is larger, and we'll explore that in just a bit. And it is vastly larger, isn't it? We've got a lot of wasted error that comes about here because we are estimating with this left-hand sum. And the right-hand sum isn't much better. The right-hand sum has got a lot of negative error, it underestimates the area by all the amount in green. Neither one of those is a very good estimate for this integral, and you can visually see that, right? What we would like to do is to cut a lot of that error out by taking each subinterval and forming a trapezoid with the endpoints. And when I form a trapezoid with the endpoints, look at all the error that I get rid of. Although the trapezoid is not perfect because it cuts across instead of following the curve, nevertheless, it cuts out 99% of the error on this curve. You see it? So just by changing my shape to trapezoids, lo and behold, I improve my accuracy without having to increase the number of rectangles or trapezoids that I pick. What a brilliant idea.
Would it be a lot more accurate than adding left sum, right sum together and divided by 2?
That's a really interesting question. Let's come back to that. Midpoint might help, right, depending upon the shape of the curve. So midpoint is often more accurate than left or right for your average curve, but there are some curves that will kind of fool the midpoint. All you have to do is to make sure that you have a curve so that you go way high on the midpoint. And so then you end up overestimating by a whole lot, or something like that. Yeah. Or way high on the ends would do that as well. So your midpoint's down here, and you miss this area.
Not full.
Well, let's actually construct the area of the trapezoids here. Let's do 1 as our representative, and then we will generalize it by summing up all of them, okay? So if I pick one trapezoid, it's going to have a width of delta x sub I, and it's going to have 2 bases that are on the left and the right. And therefore, the average of those 2 bases is going to be f of x sub I minus 1 for the left, and x sub I for the right, and the average of those will be the sum divided by 2. And that's going to be the area of the ith trapezoid. Does everybody understand what I'm saying here? Sure. Pick one trapezoid, call it I. Okay, number it I. And now its 2 bases are going to be the height of the curve on the left and the right. The height of the curve on the left is f of x sub I minus 1.
Yes.
The height of the curve on the right is f of x sub I. Average of the bases times the width. And that's the area of the ith trapezoid. And now to get our trapezoidal sum, we can simply, let's call that T for trapezoidal sum. We can simply add up from I equals 1 to n all of the areas of our trapezoids, just like that. Now this formula looks fairly intimidating, and in practice we're going to execute this formula by doing, well, you'll see in just a minute how we do this exactly. So I'll give some examples. Once I give some examples, that will provide some meaning for this formula. Right now you're kind of looking at it going, that looks scary. Am I right? But before we do that, I want to make a simple observation. Because this is a sum, I can do the usual algebra stuff to it. In particular, what I can do is I can pull out the common factor of 1/2 right there. And I can distribute my delta x to each one of these. And because it is a sum, I can add up all of these first, and then add up all of those, and add those 2 sums together. And when I do, that looks like this. But now something magical occurs. And that is that when I add up these two sums, I observe that I have seen each one of these sums before. This sum right here, the sum of f of x sub I minus 1 times delta x, is exactly my left-hand sum. And the sum of f of x sub I times delta x sub I is exactly my right-hand sum. So that when the dust settles, what I observe is that the trapezoidal sum is not superior to the average of left and right, it is the average of left and right. How about that?
What is the mathematical way of saying getting the midpoint then? How are they different, like mathematics?
The midpoint sum, if I were to express that,
Yeah.
let me write this in red so nobody gets confused here. He keeps coming back to the midpoint question. I want to answer that question. The midpoint would take the left and right x values and average those to find the midpoint, and use that averaged value to find our height.
Oh.
And then we would multiply that times delta x and add up. That's how you would construct a midpoint sum.
Okay.
And because the functions, generally speaking, don't distribute, these two are not equivalent. So this is the midpoint sum, which is not equal to the trapezoidal sum at any time, except for the special case of linear functions. Okay? All right, so what have we learned so far? We have learned so far that the trapezoidal rule at least promises to give us a much more accurate computation. It does. And that it is also equal to the average of the left and right sums, which is nice. Now, how does it actually work out in practice? I'm going to do this with a function that we can actually integrate with FTC so that we can see how good the answers are. So our first stab at this is going to be to integrate a function that we already know how to integrate. We're going to estimate that integral with a trapezoid, with two trapezoids. And we're going to compare that to the values of the left and right hand sums and compare that to the actual retail value given to us by the fundamental theorem. So here we go. Problem as stated. Find the area of the region S defined by y equals x squared, the x-axis, and the vertical line x equals 2. Go ahead and draw that region before we get started. And once you have drawn that region, represent its area with an integral. And if you're feeling particularly spiffy, go ahead and evaluate that integral with the fundamental theorem so that we know the exact answer to the question. Huh? Okay. So you should have the following things. You should have this region S right here. Does everybody have that? And you should have some points marked. You should have x equals 2 down here, and the point up here, 2 comma 4. If you didn't have those points marked, make a note to yourself that you want to mark points because they'll help keep your head straight. And now we're going to represent the area as the integral from the first x to the last x of x squared dx. How did I know that the first x was 0? Because the curve y equals x squared intersects the axis at x equals 0. Did everybody have that integral representation? Good. Okay. Emily, go ahead and give us the exact answer using fundamental theorem. Uh-oh, fundamental theorem. What does she need? She needs first an antiderivative, and then she needs evaluation.
Oh, so 1 x.
Are you sure that's the antiderivative?
Plus the.
That's an interesting question. We can take any c, let's take c equals 0. But, are you sure that's the right antiderivative? How do you be sure? Okay. Yes.
Okay.
Just because I ask the question doesn't mean you're wrong. I ask the question every time. Because we don't want to be wrong. Because we don't want to be wrong. All right. And now we're going to evaluate that from 0 to 2. And so that gives us what? I don't think so. 2 cubed
Oh.
minus 0 cubed over 2, which is 8/3. Exactly. What decimal value is that? Because we're going to get some estimations here. We want to compare them. Give me 4 places. What is it as a mixed number?
6, 6.
Yes. So 2.6667, that's our target value. Our estimate's going to be good if it's close to this, and it's going to be bad if it's not. Okay? All right. Now let's do some estimates. We're going to do a left sum with 2 rectangles to estimate. And if we do a left sum with 2 rectangles to estimate, that means we're going to need to divide up our interval from 0 to 2 into 2 equal pieces here. And of course, that means each piece would have a size of 1. Our delta x for an equally spaced left sum, right sum, or trapezoidal sum will be b minus a over n, 2 minus 0 over 2. And so we're going to compute the left sum as f of 0 times the width of the rectangle, which is 1. That's a disappointing rectangle. Plus f of 1 times the width of that rectangle, which is going to be 1. And there's our left sum right there. And we get a left sum of 1. How does that compare to 2.66667? Not even close. It's disastrously off. Okay. How about our right sum? Now, we'll cut our left sum a little bit of slack because the left sum, after all, was just 2 rectangles. So we didn't really give it much of a chance to do a very good job, right? 2 rectangles is small. Yeah, if we did 30, we'd come close. How about our right sum? How am I going to write the right sum here? Uh-huh. That's right. It's going to be height times width. But the heights now are chosen from the right. And so that's going to give me this height and that height right there. And so that gives me 1 times 1 plus 4 times 1, or 2 squared times 1. And so my right sum, where did that come from? Smart board, sometimes you're not. And so when that adds up, that gives me 5. How'd we do? That's a great. Okay. All right. How about the trapezoidal sum? Now, yes, that's right. So one way we could do the trapezoidal sum, since we've already done the left and right, is just to do left plus right over 2. So this is one option for us for computing the trapezoidal sum. If we've already done the hard work of left and right, then we get 3. How does 3 compare to our 2.666? That's not bad. That's not bad at all. Okay. Well, what if instead I had not already computed it? Then I would do it like this. I would start at my first delta x, and I would average here. I would average the left and right heights right here to get the area of that trapezoid right there. F of 0 plus f of 1 over 2, average height, times the width, which is 1. And then for the next trapezoid, I would average my 2 heights right there times 1 again. And that would give me the average height between here and here times 1. And now I can come back and I can compute that as 0 squared plus 1 squared over 2 times 1 plus 1 squared plus 2 squared over 2 times 1. And that's going to be equal to 0.5 plus 2.5, which is 3. And that gives me the trapezoidal sum, trapezoidal estimate, if I did not have the left and right already computed. Questions about that? Are we suitably impressed with the accuracy? With only 2 trapezoids, I came within 0.16. No, I came within 0.3 of a number that is somewhere around 2.6. That's not bad.
Actually, this chunk is the same as a midpoint.
No! I've gone over this like 3 times now. The trapezoid is never the same as the midpoint, because the midpoint sum takes the x's and averages those and uses that to find a height, whereas the trapezoidal sum averages the y values. Let me draw you a picture so you can see it. If I have a function like this, and I do one midpoint sum, I do one rectangle as a midpoint sum, then I'm going to go right to here, and I'm going to find that height, and I'm going to draw myself a rectangle like this, whose height is the value of the function at the midpoint, and that's my midpoint sum for one rectangle. If I do the trapezoidal, I'm going to go to the height right here, and the height right here, and I'm going to draw myself a trapezoid across there, and that's the trapezoidal. So they are not the same. Okay, let's do another trapezoidal estimation for a different function. This time what I want to do is to consider this problem. The velocity of a lab cart in meters per second is measured at various times. The results shown below. Estimate the displacement of the cart using 4 trapezoids Okay, here we go. And now we're going to have some data. And we're going to have a time given to us in seconds. And actually, I need enough space to get there. And we're going to have a velocity given in meters per second, and our times are going to be like this. And when we observe our times, we observe that whoever did the recording here didn't have a perfectly steady hand, so they were not able to use equally spaced time intervals. Bummer. That's okay. And then we've got the measurements of the velocities. What do you observe about these velocities? What's happening with this lab cart? It is what? Has negative acceleration. When does it have negative acceleration? Really?
Why don't we find out?
Now, acceleration is dv dt, right? Does this velocity ever appear to have a negative slope?
So the Germans
No, it doesn't. So it actually has positive slope throughout as far as we can tell, right?
I'm saying the acceleration is getting smaller.
Ah, the acceleration is getting smaller, yes. So the acceleration has a negative derivative, but the acceleration is not negative. You see? As long as the velocity is going up, the acceleration is positive because the acceleration is the rate of change in the velocity. But it is getting smaller. Does everybody agree with that? We accelerate strongly during the first 2 seconds, and then we taper off to basically a constant velocity.
Just to make sure it's recording.
Yes. Yep. Okay. So here is our velocity, and now we're supposed to find the displacement. Before we ever get to doing any computing, we need to represent. How are we going to represent the displacement in terms of the given quantities here? Displacement equals, first of all, what label should I give to displacement? Delta S equals the integral velocity from where to where? Over the whole thing.
Yeah.
So from 0 to 4. This is my representation, and don't you dare start a problem without representing your answer first. This is the answer to the question. Now we have to estimate the value of this integral using trapezoids. Why trapezoids? Because the directions told me to. Look for those directions. If you have to estimate an integral on the AP exam, they will almost always without exception, they will tell you which method they want you to use. Left sum, right sum, midpoint sum has been done, and trapezoid. Trapezoid is the most common because it's the most accurate. Okay? So how are we going to do a trapezoidal sum in this context? There are 2 things I need. I need average height, and I need width. So I'm going to march through my data, and I'm going to compute on the top right here, I'm going to compute the delta t's as the difference in each one of these time intervals. 1.3 minus 0, 2.1 minus 1.3, 3.3 minus 2.1, 4.0 minus 3.3. And I'm going to actually write those values right there, and I like to write them with a little bracket right here to indicate that I'm doing a time interval delta t. Does everybody see what I'm doing? Okay. Now, for the average heights, I'm going to march through and I'm going to average by hand these values. The average of 1.5 and 2.8. 3.3 divided by 2. 1.65. Is that right? No. 3.3. It's 4.3 divided by 2, so that's going to be 2.15. Is that better? 2.15. Yep. I'm on 3 hours of sleep. All right. Average of 2.8 and 4.2. 3.5. Yep. Average of 4.2 and 4.5. 4.5. average of 4.6 and 4.5, 4.55. And now I can say that this integral is approximately equal to, it's not equal to, but it's approximately equal to average height times width. 2.15 times 1.3. I'm going to need some room. Plus 3.5 times 0.8 plus 4.35 times 1.2 plus 4.55 times 0.7. And what units go with that? It's going to be the units of the velocity, meters per second, times seconds. What do I get when I multiply meters per second times seconds? Meters. Is that a good unit for displacement?
Sure.
Yeah. So all that is going to be in units of meters. And I can simplify that if I want to, but I don't really want to. Let's do a quick estimate in our heads. This would be approximately about 2 plus 2 plus about 4 plus about 4, a little bigger than that. So let's call this 4 here plus another 8, maybe 9, so about 13, somewhere like that.
What notation exactly do we use? Do we go with that one, or do we go with like the one that looks like this?
The summation notation, you can do either one, but in the end, when you actually compute it, you have to write out each of the terms, right?
Okay.
So the summation notation is a convenient way to take all of this right here and just roll it up to a one convenient notation. But it doesn't actually do any computing for you. To compute it, you have to unroll it and do each term at a
So
time.
you just write the summation notation instead of done as
You could. They would understand that and accept that, but it doesn't do you any good computation. Are there questions on this? What's that? What is it? Well, it's the displacement, see? It's got a label.
Why do we use this?
I don't know, actually. It's commonly used.
It's like this.
All right. You try it. Get your calculators. Go. What's that?
You should just do it again.
You can compare your answer to the calculator answer when you're done. Yeah.
Are we allowed to graph it?
You can if you need to. What is my delta x going to be? 2, right. It's going to be 6 minus 0 over 3. Equals 2. And so now I can write the trapezoidal estimate as, what's my first trapezoid going to look like? What's that?
0 to
It's gonna go from 0 to 2, so how am I going to estimate that?
1, 2. F of 0 plus f of 2 over 2.
Over 2 times the width. Exactly right. And the next one?
F of 2 plus f of 4 over 2 times 2.
And the last one?
F of 4 plus f of 6 over 2 times 2.
And so when we do the estimate, we're looking at e to the negative 0 squared plus e to the negative 4 all over 2 times 2 plus e to the negative 4 plus e to the negative 16 all over 2 times 2 plus e to the negative 16 plus e to the negative 36 all over 2 times 2. Now when you add them all up, what do you get? No, it's gotta be bigger than that. Because this is 1 plus e to the negative 4. Yep. Okay, so what was that? I don't know. I was messing with my calculator. E to the negative 4 is, huh? That was strange. I think it interpreted that as multiplication. E to the negative 4. There we go. 0.0183. What was e to the negative 16? Pretty darn small, I would guess. It's almost 0. Uh-huh. Yep. Yep. And this guy turns out to be horrendously small, right? So that the whole term is basically 0. And so now when you add them up, you get 1 plus 0.0183 plus another 0.0183 is 1.0366 as the estimate for the interval. What was the actual retail interval?
0.886.
So our trapezoid overestimated the area? Really?
0.8862.
Okay. That actually surprised me a little bit. Let's talk a because you used a subtraction instead of an
Oh, I did. Oh, wow.
Yep, 0.8862. Yep. All right, so we overestimated it a little bit. Now, in terms of overestimating and underestimating, I want to speak to this for just a minute. If the bell rings, give me half a moment to do this. I want to talk just a little bit about the errors that you can get from our estimations. And I want to use the shapes of curves as a way to argue plausibly for this. Let's consider 3 different methods: left, right, and trapezoidal. And I want to consider whether they over or underestimate the value here. First of all, let's consider the case where f is an increasing function. And for that, let's draw ourselves a graph of an increasing function. There's an increasing function like that. If I go on the left-hand side, take a look at my rectangles. Every single time that f is increasing, my left-hand sum is going to underestimate the value of the integral. You see it? And likewise, if I do a right-hand sum, every single time that right-hand sum is going to overestimate the value of the integral. What about a trapezoidal sum? The trapezoidal sum is tough because some curves increase like so, but some curves increase like so. And this trapezoidal sum overestimates, and that trapezoidal sum underestimates. So just by knowing increasing or decreasing, I don't necessarily know whether I'm going to get an over or an underestimate. Tell you what, let's finish this chart up tomorrow. But I think we'll need a little.
What's X again? You don't know?
Yes.